Anybody have any questions they want to ask from last time?
On the homework, can you do problem 19 for us?
Make a comment while you think about it. I was gonna have an extra credit quiz tonight, but, the way things have worked out, let's do our extra credit quiz next time. So extra credit quiz, will be on Monday. Be worth, just 10 points. The object is to see if, want to keep you up, but then also to see if we can send email out in the form of a test and get an email back. That's how the first test is going to be, is by email. So at the end of class on Monday, not today, I'll send out an email and you can send it back within 15 minutes or so that I'll give you, just to try it out. If you have troubles, then we'll get them worked out this time before the actual tests come up. Any other questions come up then? Anything you want to look at?
On the homework, can we do problem 19?
All right, well, today, well, I better start off with something better because this is more convergence test. This is the most boring part of the course, but the good news is it's only going to get better, right? Just like this COVID thing. Here's a good question for you. This is a math question, not dealing with calculus. A bear walks 90 feet south, then 90 feet west, then 90 feet north, and arrives back where it started. How can this be? No, I'm sorry. That's not the right question. What color is the bear? How about that? Anybody heard this one before? It's a math question. Well, the object say, where on earth can you walk 90 feet south and then 90 feet west and 90 feet north and wind up back where you started? Right? If you start at the North Pole, right? So if you go 90 feet south and then 90 feet west and then 90 feet north, then you wind up back at the pole. So it must be a polar bear. It's white, right? So there's the first question for today. That'll wake you up, hopefully. All right, the rest of the class then will be calculus. And here we have more convergence tests, and we're going to go back and review some of the ones we did. All right. With high-speed computers, sometimes half the battle is just knowing it converges. Then you can estimate it with the computer, right? Well, here's, we did a number of tests already. We did the integral test. We did the comparison test, the limit comparison test. We want to do this one now. Let's say, but this is probably the most important convergence test of the semester. It's called the ratio test. And it goes like this. Suppose a series that you write up, sum n equals 1 to infinity, un, has positive terms. Each un is bigger than 0, right? Let then rho be the limit as n goes to infinity of the ratio of two successive terms, un plus 1 over un. Then there's three cases, really two. If rho turns out to be less than 1, could be as little as 0. If this exists and is less than 1, then the series converges. However, if rho is greater than 1 or is infinity, can't be minus infinity, it's all positive terms, right? So don't have any negative values. Then the series diverges. The book puts a third case. If rho equals 1, you don't know. I kind of like to leave this one out because it doesn't say anything. But if rho equals 1, let's say just to follow the book, it could be either, depending on the series. How about that? This turns out to be the most useful test for some series that we're coming up on, called power series, which are a very important tool in lots of mathematical sciences. All right, so there's the theorem. I want to make a note on this. This test is really great and often used when n factorial or a number a to the n or both is in the nth term. Here's an example why. Suppose I look at this one and I say, I wonder if this converges or not. Sum n equals 1 to infinity of 2 to the n over n factorial. These are both really fast-growing functions, right? 2 to the n is exponential growth, right? It's doubling 1, 2, 4, 8, 16. This is faster than any power of x you remember from calculus 1, right? 2 to the n grows faster than n to the 1,000th power, for instance, right? It goes faster than any power of n. Exponential growth is really fast. And factorial is really fast too. It's 1 times 2 times 3 times 4. Maybe we should write out what it is. This symbol means n times n minus 1 times n minus 2 times n minus 3, all the way down to 2 times 1, all multiplied together. It's called n factorial. Maybe you've seen it before. There we go. How about this then? It's got a very fast growing term on top and a very fast growing function on the bottom. If you really think about it, it looks like the bottom is growing faster. So maybe this converges, right? But it's not sufficient to know that these things are the quotient is getting closer and closer to 0, right? I mean, on the top, every time you increase n, it multiplies it by 2. But on the bottom, when you increase it by n, it multiplies it by n. So you get 2 squared over 2 factorial. And then you get times 2 on the top and times 3 on the bottom and times 2 on the top and times 4 on the bottom. So the bottom is getting big faster than the top if you think about it. But is it getting bigger fast enough that the sum is finite? Maybe it's actually infinite, like we saw last time, this harmonic series, sum 1 over n running from 1 to infinity, which is also 1 plus a half plus a third plus a fourth on forever. The terms are getting smaller and smaller, but this gets bigger than any positive number. There is no upper bound on it, and so we say the limit's infinity. You can make it bigger than any number you want by going enough terms. Maybe this one's the same. Here's how you can deal with it. When you see powers of a number or factorials, this is a really good test, the ratio test. And it works for other cases too, actually. but this is to me, the most important one. What we do is we say, well, these are positive terms because this is positive and this is positive, their quotient is positive. So we got that. Now, as the limit as n goes to infinity, the nth term equal to 0. What's the limit of the quotient term? Limit as n goes to infinity, put it down here. Of, we put the nth term on the bottom, so we just copy this, 2 to the n over n factorial. Then we put the n plus first term on the top. The way you do that, I'm going to get rid of my n factorial now. I need the space. This is another lesson from this class. I always plan ahead. All right. What you do is you put parentheses everywhere you see n, and then you put in n plus 1. And this is un plus 1 over un as in the theorem. If this limit is less than 1, could be 0 even, then the series converges. If this is bigger than 1, it diverges. If it's equal to 1, you can't tell. But this is just like functions, right? If you have f of x equals x squared, what's f of x plus 1? You put parentheses where x was, parentheses squared, and put x plus 1 in, right? Same thing here. Un here is just a function of natural numbers, n, right? So again, you just replace n by n plus 1 to get un plus 1. There it is. This is what it looks like. Now, here's why this works well for powers and factorials. 2 to the n plus 1 can be written as twice 2 to the n, right? I'll pull a factor 2 out of there. Right? 2 to the 1 times 2 to the n is 2 to the n plus 1. N plus 1 factorial, if you think about it, means the numbers 1 through n plus 1 multiplied together. So it's n plus 1 times n minus 1 all the way down to 1. Well, that's n factorial, right? This is the numbers 1 through n multiplied together, and then times n plus 1 is n plus 1 factorial. So I'll factor in n plus 1 out of this one, times n factorial, looks like that. Now the bottom is 2 to the n over n factorial, and now you recognize, right, these are both denominators, I can cancel those. These are both numerators, I can cancel those. This is all canceled out. All I have is 2 over n plus 1. So this is the limit as n goes to infinity of 2 over n plus 1. Now bear in mind, this isn't a series we're talking about anymore. We're saying, is the limit of this sequence less than 1 or bigger than 1? And you can see what it is, right? If I said, what's the limit of 2 over x plus 1 in calculus 1, you would have said, oh, it's 0, right? Because the bottom is going to infinity, but the top is going to, is equal to, in fact, 2. 2 over bigger and bigger numbers, the limit is 0, right? The limit is 0, according to the theorem, the series converges, right? Any limit less than 1, it means it converges. So the conclusion then is convergence by the ratio test. Since rho is less than 1. In fact, it's equal to 0. So there's the ratio test. You can see how when you have powers or factorials, things cancel. Well, here's another test. If you want more examples, don't worry, there's more coming. I'm just trying to get all the tests together because the real trick is to be able to have all these different series and all these different tests and be able to figure out which test to use, right? Know which tool to take out of the toolbox, right? Tool for the right job, it's all right. So now here's another theorem, the root test. This section is about convergence tests for a series of positive terms or at least non-negative terms. So you'll see every one of these, it says, let this have positive terms or let this have non-negative terms. This one, like the last one, is for positive terms. The root test says this. Suppose an infinite sum has positive terms. And when I say UN greater than 0, that means for n equals 1, 2, 3, forever. That's what the theorem says. But remember, we said before that any finite number of terms doesn't affect convergence. So actually, some of these can be negative. And in the last theorem also, you can get negative numbers, as long as when you take out a finite number of them, the remaining ones satisfy this test. So all these tests we're presenting, the series just have to satisfy the criteria eventually. Eventually, terms have to all be positive and satisfy the following criterion. So suppose the terms are positive, then let this time rho, the same Greek letter, be the limit as n goes to infinity of the nth root of the nth term. Then the same conclusion holds. 1, if you get a number, rho less than 1, then the series converges. By the way, there's no problem taking this root because there's no negative numbers. You don't have to worry about an even root of a negative. So if rho is less than 1, just like the last test, the series converges. But if rho is bigger than 1, it diverges. Or if it's infinity, the series diverges. And then if you want, you can add this third extra step that says nothing. If rho equals 1, the series may converge or diverge. Right? Every series either converges or diverges. It says nothing, but it does remind you that we just don't know if it's equal to 1 what to do. All right. Well, if you came in late, I said we're going to do our extra credit quiz next time. So make sure that next time you're able to either you're able to print out your test or look at it on your phone. It's just a quiz, and then either scan it in or take a picture and send in the scan or the picture to me at the end of class, and I'll give you up to 10 extra points. It's just a practice for being able to take the test later. Here then is an example problem for this one. There we go. Sum k equals 1 to infinity of k over 10 to the k. The root test is not such a useful test. It's rarely used, actually. But where it shines is when the kth term is a kth power. Because the root, when you take rho to compute the root, it'll take the power out. So we should make that comment. The root test is useful. Sometimes other times, but especially when UK, the kth term, is a kth power, or a 2 kth power, a 3 kth, because it's still a kth power also. And the 3 kth power is the third power to the kth. And that's what we have here, k over 10 to the k. So we compute rho, we first notice these terms are positive, right? Because k is positive, 10 is positive. The quotient's positive, then you take a positive power, it's positive, right? So positive terms are the first criterion. Now you try the root test, limit as k goes to infinity of the kth root of the kth term. Well, the kth term is k over 10 to the k. And now you see the beauty of the root test. The kth root undoes the kth power, and you get the limit as k goes to infinity of k over 10 and say, oh, that's going to go to infinity. So this one diverges. All right, since rho is greater than 1. That's the last two tests of importance out of this section. Now I want to go back and these comments are useful. Say, suppose I give you some random series, which of these converge, which of these diverge, and you pick any test you want. All right, how about this one? Sum k running from 1 to infinity, 1 over 3k squared minus k. The object of this is just practice, right? You start to get a feel for what test you use. Here's the first thing that comes into play in these is you get some intuition from that p-series test. If you have a series where the terms go to 0 like 1 over k or slower, then you know instantly it diverges. If they go like 1 over k to a higher power, then it's going to converge. So I look at this and I can, from it, make a pretty good educated guess without even computing it. A test here. Because you say, what does this look like? For large k, this looks, we'll say asymptotically like 1 over 3k squared, right? That is the kth term. Now, if that was that's the terms, that would be 1/3 of a p equals 2 series, right? Sum 1 over k squared is the p series with p equals 2. And 1/3 doesn't affect convergence. It just makes the series 1/3 of what the 2 series would be. So I think it's going to converge. That intuition is immense, right? If you don't know whether to try and prove it converges or diverges or what test to use, it can be quite difficult. But once you see it looks for large k like 1 over 3k squared, that suggests that you can compare it either with a comparison test or a limit comparison test, right? But I'll try and prove convergence because this one converges, and for large k, these two look about the same. I'm going to try the limit comparison test from last time. Remember that one? The reason I do that is it looks asymptotically like something. If for large k it looks like something, you can do a limit comparison with that. Or often a comparison test too. The comparison test would work on this one. I just think the limit comparison, oops, probably easier. Hope I don't make you dizzy here sometimes. Now, here's what we do. Limit comparison test with my intuition series, sum 1 over 3k squared. Or any multiple of that. Let's do the simple one. Sum 1 over k squared. It's just 3 times that series. We can still do a limit comparison if it's 3 times that. What do we do for the limit comparison test? This is where it starts to get confusing and you just have to do the practice because this one also has a rho in it. Remember, rho is the limit as k goes to infinity of the kth term of one of these with the kth term of the other. It doesn't matter actually which one you put on top. Let's put this one on top, 1 over k squared, and put that one on bottom, 1 over 3k squared minus k. In this test, if this comes out to be any finite number whatsoever, then they either both converge or both diverge. And I know this one converges, so that'll prove that one converges. It's different than the ones we just did today, right? On those, when you pick rho, if rho is greater than 1, the series converges. If rho is less than 1, the series diverges. I understand this is confusing at this point. It's easy just to get mixed up series and sequences even, right? A sequence is a list of numbers like this. This is a sequence. And a series is an infinite sum of numbers. Right? So here's a sequence and here's a sum. And just to remind you, right, to see if a sequence converges, what do? we add up the first n terms, a1 to an, and then it's the limit, and we say the sum of the series is limit n goes to infinity of Sn, the sum of the first 10 terms, and that's how you decide if this converges. How do you decide if this, I'm sorry, this one, use your calculus forms, and this one, you add up the first 10 terms, sorry, u1 to un, get a formula for them, and then if the limit of this one is a sequence exists, then you say that's the sum of the series. The sum of this series is the limit of the sequence of partial sums. And this one you usually use calculus 1 to prove it. You just put the corresponding continuous variable. All right, and then we do have two special cases. We have geometric series, telescoping series, where we can actually calculate the sum, not just see whether it converges. All right, so I'm just reminding you, sequences are like that, series are like that. All the things we're doing tonight are for series, right? We mostly introduced sequences to be able to do these things with series. So to take this limit now, I'll multiply top times bottom over middle times middle, right, just by fractions. 3k squared minus k over k squared. And say, now what's that limit? Well, it's 3, right? Because for quotients of polynomials, the limit depends on the dominant term. Since they're the same power, right? The limit exists and is equal to the quotient of dominant terms. 3 over 1 is 3. You don't say like you would have with the ratio or root test that it diverges. This row just shows they both converge or both diverge. Right? So I now say, since our comparison series, sum 1 over k squared, k running from 1 to infinity, converges by the limit comparison test. We take this limit comparing the two by ratio. So does our original series, 1 over 3k squared minus k. So there's one way, I think the easiest way, to show that this series converges. Do a limit comparison test with this easy series that you memorized converges. It's a p equals 2 p series. Is why we know it converges. Some of these series, if you look at your syllabus, actually converge to some very interesting numbers. Some of these series that look kind of awkward actually converge to pi or natural log of 2, this kind of thing. And it's kind of surprising sometimes what some of these things add up to. All right, any questions on that one? Yeah, I will make a comment that on a lot of these, you can use more than one test. Just some of them are easier than others. I think this is the easiest one. But suppose instead of doing a limit comparison test, we tried to do a comparison test. You'll see why I wanted to do the limit comparison test instead, because this will be harder. Show by the comparison test this time, not the limit comparison test, that this same series, sum 1 over 3k squared minus k, k running from 1 to infinity, converges. This means, the comparison test, that I have to compare it with another series that converges where the terms are all bigger. Or since all these apply in the eventual case, they just have to eventually all be bigger. So suppose I had decided to use the comparison test. Here's what I could have done. Compare sum 1 over 3k squared minus k with a series we know converges. Well, we'd like to say, put something with smaller denominators, and then if it converges, and then this one converges, because smaller denominators means it's bigger quotients. Right? Compare it with this, and here's the trick, is to be algebraically clever. Right? It's better to use the limit comparison test so you don't have to be so clever. I'm going to compare it with 1 over 3k squared minus k squared. Why would I do that? Can you see it? This denominator is smaller than this one, right? This is a smaller denominator because k squared is bigger than or equal to, I should say less than or equal to. K squared is bigger than or equal to k. So I'm subtracting a larger number or equal number. This one has the bigger denominator. All the terms are positive, right? This is a positive number because you put in 1, you get 3 minus 1 is 2. Put in 2, you get 12 minus 1. K squared gets big faster than k, so this is always positive. You can check this one's always positive too, because it is in fact this series. Sum k equals 1 to infinity, 1 over 2k squared. Right? I picked k squared here so I can subtract them easy and get an easy series. So this one has bigger denominator. It is smaller. Smaller denominator. What am I saying? Bigger k squared, smaller denominator. Mix you up here. Because you're subtracting a bigger number, it's a smaller denominator. That means the quotient is a bigger term in the original series, bigger than or equal to. Let's write that on there. Smaller denominator means a bigger quotient for positive quotients. And so now we have shown that 1 over 3, let's say as big or bigger, the first term might be equal, I think. As big or bigger. All you need is eventually bigger, actually. But 1 over 3k squared minus k is what we've shown is actually less than or equal to 1 over 2k squared. All right. This series, each term is less than or equal to this one with positive terms. Now the sum of the bigger series, 1 over 2k squared, k running from 1 to infinity, is pull the 1/2 out. It's 1/2 of the p series with p equals 2, right? 1 over k to the p is the p series. Oops. So this is a p equals 2 series. Remember, a p series converges for p greater than 1. I told you that p series is very important for intuition. And so this converges. So we have a series whose positive terms are less than or equal to a convergent series. Therefore, our original series, sum 1 over 3k squared minus k, also converges by the comparison test. Let's see some questions on that one. But you can see if you use the comparison test, you usually have to use some clever algebra. Sometimes it's obvious, but usually it's clever algebra. If you use the limit comparison test, it's easier. It gets rid of all that algebra. But both of them work and are used, frequently in analysis. So use whichever one you want. By the, can't talk and write sometimes, right? By the comparison test. Never could rub my tummy and pat my head at the same time. That's sort of, but not really. So there's a second way to do it. All right, let's try some other series. Let's move this to the other end. No questions yet, huh? Let's have to go faster. But the object is to be able to look at the series and see which test to use. I call this the duck strategy. I've told one of my classes at least so far this. When something looks like a duck and quacks like a duck and waddles like a duck, it must be a duck, right? So this looks like a 1 over 3k squared eventually. You can do a limit comparison test with the series sum 1 over 3k squared, which we know it converges. So that's what you do, is you do the duck test here. You use intuition and say, what does it look like? And a lot of times that tells you what test to apply. It looks like it has powers and factorials, ratio test. It looks like it has kth power of everything, root test. It looks like a 1 over k squared, or 1 over k to the 10th, or 1 over k to the square root k. That's a good comparison or limit comparison test. That's what we're finding out here now. Let's try this one. Suppose I had sum k equals 1 to infinity of 2 over k minus a half. What's my intuition tell me on that one? What does your intuition tell you? This is the duck test again. What does it look like, right? This looks asymptotically like 2 over k, right? Because this one will be much smaller. As k gets to a billion minus a half is about a billion, right? And so for large k, it looks about like 2 over k. So that suggests I could limit comparison with 2 over k. So let's do that. Let rho equals, you can put whichever one, the quotient of these two things, and you can put whichever one on top. So limit comparison is what I'm doing. In this test, I let rho be the ratio of the two kth terms. So I'll let rho be this one, 2 over k over this one, 2 over k minus a half. Limit, I'm sorry, as n goes to infinity. Okay. A limit comparison test, you can take the comparison series divided by the original one, or the other way around, it doesn't matter. And let's see, the 2's cancel, right? They're both numerators. Top times bottom over middle times middle gives me k limit of k minus a half over k. Well, it's quotient of polynomials, so it's quotient of dominant terms, which is 1 over 1 is 1. This is not the ratio or root test where it tells you nothing. This is the limit comparison test. When rho exists, that's these series, with these terms on these series, they can either both converge or both diverge. Right? So since we know this series, right? The series 2 over k, k equals 1 to infinity, does that converge or diverge? I know that one easily. What is that? Pull the 2 out, that doesn't affect convergence. That just doubles the sum. What series is that? Harmonic series, right? 1 plus 1/2 plus 1/3 plus 1/4. We know that this one is infinity. So what we find out that this sum adds up to infinity. That is, it diverges to infinity. And infinity is a symbol that means it diverges because the terms get bigger and bigger without bound. That's what writing that means. Well, if this series diverges and the comparison test applies because the limit of the quotient is 1, therefore, the original series, sum 2 over k minus a half, diverges also. And now you start to see how you can look at this thing and tell these terms look just about like twice the harmonic series. You can imagine this in your mind once you practice this for a while, right? If it's twice the harmonic series, it diverges, right? And the limit comparison test proves it. Oh, good. Any questions at all? Sometimes I worry the camera's gone off. It looks like it's still on. All right. I hate talking to the walls and there's actually nobody online. That's happened. All right. Let's try this one. Sum k equals 1 to infinity of 1 over 2 to the k plus k. Bear in mind, on most of these, there's more than one test that you can apply. Does that converge or diverge? Again, if I do the duck test, I can say, well, this really looks like asymptotically that this 2 to the k is an exponential. It dominates k, right? This grows faster than the power of k, in fact. So this ratio looks asymptotically like 1 over 2 to the k. Asymptotically really means that the limit of the ratio of this to this is 1. And that's what we're going to find. So I'll say this looks like 1 over 2 to the k for k large, because when k is a billion, 2 to the billion plus a billion is, to a lot of significant digits, 2 to the billion. So let's compare it with this one, compare it with this one, since the duck test says we got 1 over 2 to the k. We'll take rho, again, equals limit k goes to infinity of the comparing one. You can put whichever one on top on this test, not on the root ratio test, but on the limit comparison test. There's the comparing kth term divided by the original kth term. And if this is a finite number, I should have put on here last time too. I maybe didn't put, this has to be a finite number greater than 0, then they both converge or both diverge. So if this gives me if this is between 0 and infinity, converges, then these exist, then these series both converge or both diverge. So we'll just see if this limit is a number between 0 and infinity. And sure enough it is, because now we've got by algebra, this is 2 to the k plus k over 2 to the k, right? Top times bottom over middle times middle. And the limit of the sum can be written as the sum of the limits, provided they both exist. So it's 2 to the k over 2 to the k is 1, plus k over 2 to the k. But this is easy, actually, right? This is limit k goes to infinity of 1, plus limit k goes to infinity of k over 2 to the k, provided they both exist. But they do. This one is an easy one by L'Hopital's rule. If you think of this as x over 2 to the x, my derivative of this one is 1, and this one comes out ln2 times 2 to the k. So by L'Hopital's rule, or as far as I'm concerned on this one, you saw in calculus 1 that the limit of any polynomial, here's k to the first, divided by an exponential with base bigger than 1, is driven to 0. So you remember that polynomials divided by exponentials are driven to 0. So this limit is 0. Again, use L'Hopital's rule if you want. You can say this one is equal to the limit k goes to infinity of the derivative of the top 1 over the derivative of the bottom, ln2 times 2 to the k. And now this one's going to infinity, and the top's 1, and so you say the limit's 0. So you can prove it with L'Hopital's rule. You just remember polynomial divided by an exponential with base bigger than 1. The limit's 0. So this whole thing, the limit is 1. The limit is a positive finite number. They both converge or they both diverge. But I compared it with a very simple series, right? We'll say now the series 1 over 2 to the k, how do I know if that converges or diverges? You have good intuition, because 2 to the k grows fast. It's certainly going to grow faster than 1 over k squared. You can make an argument for that. It's true. But even easier, this is a geometric series, right? This is the sum k equals 1 to infinity, 1 times 1/2 to the k. It's a geometric series with a equals 1, r equals 1/2. When r is between -1 and 1, you get convergence. So it converges. Maybe this is the easiest way to do it, I think, is that notice that it's a geometric series. we can even compute this sum. So this one converges, therefore, the other series, sum k running from 1 to infinity, 1 over 2 to the k plus k, converges also. Not for the same number, because it's adding up different terms, but it converges also. But that's the idea. You use intuition and say, boy, this term goes so much slower than this one. This looks like 1 over 2 to the k. Geometric series, right? And so you just see that in your mind after doing enough of these, and then it all works out nicely. So I hope this is making the thing seem easier for you. On the first test, I'm going to give you some of these things like this, some questions. I should announce today also, as of the current moment, and I think it's going to stay that way, we will begin meeting in person on Monday. So those people who would like to come to class, who are feeling well and haven't been exposed to COVID recently, are welcome to come to class in person. The size of this class is such that even if you sign up for online lectures only, there's plenty of room to spread out in here. So if you want to come to class, whether you're signed up either way, come to class. If you want to stay home, you can stay home all semester. I certainly agree with watching it on TV to save catching COVID. So beginning on Monday, you can come to class or you can stay at home, and I'll work it both ways. We will have our first test online by email. And on Monday, if you're here, I'll give you the test in class, the quiz. And if you stay home, then I'll send it by email. And you can take it that way, either way. And it'll be an open book test. So if you come to class, bring your book and notes and whatever else you want to work on the quiz. All right, here's another series. Suppose I said sum k equals 1 to infinity. I thought this was kind of a tricky one. It's very similar to one of your homework problems. Cosine squared k over k factorial. Now this is getting tricky because remember the cosine function oscillates as a wave. You got something wobbling up and down. What happens? Well, this is the square, so it's non-negative. We can apply our test for non-negative terms. But it still wobbles up and down forever. It never settles down. Fortunately, it's divided by k factorial, which grows very fast. Our intuition says if you have something that's on the order of 2, right, this number is always between 0 and 2, because cosine is between plus and minus 1. The square is between 0 and 1. Multiplying to the numerator is between 0 and 2. This is intuition. Divided by a fast-growing function, we expect it to converge. So I'm going to try and write a convergence test here. This is what you don't catch from the book, is some of this intuition, I think, or any book. So what can I do? When you have something that wobbles, a good idea is to do a comparison or a limit comparison. So we can try either one of those. We can say, well, these look about like, well, I see a factorial. Maybe I should use a ratio test. I could do that kind of thing. I could say this. Let's do a comparison test with the upper bound on this, sum k equals 1 to infinity of 2 over k factorial. After all, every term in here is less than or equal to these, right? So I can do a comparison test. Comparison test, you have to have non-negative terms, and they are. What is this one? It converges by the ratio test. The ratio test for this series, not our original one, is you take rho equals, the limit as k goes to infinity, of the k plus first term. Remember how to get that? You just replace k everywhere with k plus 1. 2 over k plus 1 factorial over the kth term, 2 over k factorial. So there's the limit of the ratio of the k plus first term to the k, excuse me. And now because we have factorials in here, stuff is going to cancel. And we notice the 2's cancel. This is the limit. K goes to infinity of k factorial over k plus 1 factorial. And now remember k plus 1 factorial. I'll write it out this time, I have more room. Is k plus 1 times k minus 1, all the way down to 1 multiplied together, right? But this stuff is k factorial. Right? So k plus 1 factorial is k plus 1 times k factorial. I'll write it that way. This is now the limit as k goes to infinity of k factorial over k plus 1 times k factorial. Now the k factorials cancel. Limit of 1, if you like, multiplying that over k plus 1 is 0. When rho is less than 1, and it's 0, the ratio test says this series converges. So this series here converges by the ratio test. Since our original series has non-negative terms, 2 times cosine squared k over k factorial, less than or equal to these 2 over k factorial, and the latter series converges. This one also converges by the comparison test. Its terms are non-negative terms less than or equal to those of a convergence series. So therefore, the sum 2 cosine squared k, k running from 1 to infinity, I'm out of room, converges also by the comparison test. How about that for a trick? You had to do 2 of them. This is how you often can deal with series that wobble up and down, and you just get something that's big enough to trap the whole wobble, and so that it converges, and so the wobbly one converges also by comparison or limit comparison. So I hope you're getting a feel for a lot of the tricks that apply on these things. That's the object tonight. And we're just about done with all these boring convergence tests. We'll have lots of fun later in the semester, lots of neat pictures in 3 dimensions, and Calculus 4 continues that, so. All right. How about this one? Suppose I have the sum k equals 1 to infinity of 1 over the cube root of k squared plus 2k. How about that? What do I think on that one? Well, here's an idea. Use essentially intuition. What does this look like for k large? K squared dominates 2k, right? The square dominates any multiple of k. And so this looks asymptotically like the cube root of k squared, and then with one numerator, and you include the top. This look, oh, wait a minute, that's a 1 over k to the 3 halves. So I could try and do a comparison test or a limit comparison test with this series. So try this series, sum 1 over k to the 3 halves, k equals 1 to infinity. Does that converge or diverge? It's easy, right? This is a p series with p equal 3 halves. 3 halves is bigger than 1. Since this p series converges by the p series test, and put it here, and if you take the limit as k goes to infinity of the ratio of this compared series, 1 over k to the 3 halves, with the original series, 1 over k squared plus 2k to the 3 halves. Top times bottom over middle times middle is limit k goes to infinity of k squared plus 2k to the 3 halves over k to the 3 halves. And you can write that as one big ratio. It's limit k goes to infinity of k squared plus 2k over, oops, this was, yeah, over k. I wrote this wrong. It's 2/3. I just boxed this up. You guys got to interrupt me. I'm not going to need to talk even when I box it. This is k to the 2/3. All right. And so I'm going to compare it with, I'm going to limit comparison it with k to the 2/3, which diverges. One off the test. Now I'll put in my plug. I usually put, always check your answers on the test. A lot of you do better than me on your tests because I'll go through and I won't check all my answers until I go grade the thing and then I'll catch my errors. So if I go back and check all my answers, though, I get them all right. So if you check your answers, you'll get better scores. Here's checking my answer. That should have been k to the 2/3. That diverges p series with p less than 1, right? So we're comparing it with something that diverges. We're hopefully going to prove this one diverges also. All right, so now it's 1 over k to the 2/3 over 1 over k squared plus 2k to the 1/3. Is what I should have written. Now what I have is, this is k squared plus 2k to the 1/3 over, this one is k squared to the 1/3. All right. Top times bottom is this one, middle times middle is this one. Now I've got it. Cube root over cube root, I can combine them, right? This is the cube root of k squared plus 2k over k squared, all to the 1/3. And remember what you can do with these? Provided the limit exists of a continuous function, you can pull the limit inside here. So this is a continuous function. Provided the limit turns out to exist, this is justified. I can take parentheses limit k goes to infinity of k squared plus 2k over k squared, whole thing to the 1/3, if this exists. All right. Well, it does, right? Quotient of polynomials of the same power, the limit is the quotient of dominant terms, it's 1 to the 1/3 is 1. Right? Since rho equals the limit of the compared series and the original series is any positive finite number, therefore they both converge or both diverge. This is the limit comparison test. Right? So therefore, move this over, I suppose, huh? Since this series diverges and the limit comparison test says they both do the same thing, therefore our original sum k equals 1 to infinity, 1 over cube root k squared plus 2k diverges also. But it all comes down to this intuition. You look at it and you say, hey, that looks like 1 over k to the 2/3. I know that diverges by the p series. That's how you attack all these problems. And it works pretty well. Go to the other side. How about this one? Suppose I took the sum of 2k plus 1 over 3k minus 1 to the 2k's power. K running from 1 to infinity. How can I show that converges or diverges? Anybody got an idea they want to put in? It is recorded, but so I know that makes it harder. when you see a kth power, think of the root test, right? I'm gonna rewrite this as sum k equals 1 to infinity, 2k plus 1 over 3k minus 1 squared to the kth power, right? A to the b to the c is a to the b times c. That property from algebra. So I'll pull that k out, and now I have a kth power. So I'll say by the root test, what I need to do is take rho equals the limit as k goes to infinity of the kth root of the kth term. Kth root, and by the way, you also have to say that these are positive terms, but they obviously are, right? This is a positive number for k bigger than or equal to 1. So is this one. So the ratio is positive and the power is positive. You intuitively know that, right? All right, so this is the kth root of the kth power, 2k plus 1 over 3k minus 1 squared to the k. And the kth power and kth root undo each other. Its limit as k goes to infinity of 2k plus 1 over 3k minus 1 squared. Well, what's that limit? Easy, right? Provided it exists, you can pull the limit inside the square, and you say this is the limit as k goes to infinity of 2k plus 1 over 3k minus 1, all squared. And we know this one, again, it's quotients of polynomials with the same power, so it converges to the dominant, the ratio of dominant terms, 2 over 3. So this one heads to 2/3, that's the limit. And what we get is 2/3 squared, which is 4/9. That's less than 1. The ratio test says if rho is less than 1, then the series converges. Not ratio test, I said the wrong thing, root test. All right. The root test takes the kth root. The ratio test takes the ratio of successive terms. The comparison term compares two series, trying to show that one diverges because the other one does, or one converges because the other one does. And the limit comparison test does the same thing, just as a limit of the quotient of terms. Those are the main series we have. We also have the divergence test, which is very easy for some basic cases. Suppose I have this one, sum k running from 1 to infinity of 3k plus 1, minus 1, sorry, over 3k plus 1 squared. Does that converge or diverge? This one, your intuition tells you this. The terms are not getting smaller and smaller going to 0. Last time we said that was the divergence test. If any convergence series, the terms have to get smaller and smaller approaching 0. Right? You can't have them some finite value or the series will wobble, wobble, wobble forever. Won't ever add up to anything. So we look at the kth term since the kth term has limit. So we're taking the limit of the kth term, not the sum of the series. This is 3k minus 1 over 3k plus 1 squared. Again, we can pull the limit inside here, and then the limit is the quotient dominant terms is 1. Or if you like 1 squared. The limit of UK here isn't 0. This series diverges by the divergence test. Divergence test says if the limit of the kth term as k goes to infinity isn't 0, it can't converge. How about this one? Suppose I have the sum k running from 1 to infinity of minus 1 to the k over 2 to the k. How about that? This one has a problem. We've been doing our series for with positive terms, but this one oscillates between plus and minus. We're going to have more to say about these shortly, but how could I show this one converges with the things that I have? Well, I can say this. Since the sum k running from 1 to infinity of 1 over 2 to the k, right? Has terms bigger than or equal to this one, right? So these terms are at least as big as this one. Let's say since this converges, this one will also. Maybe I'll put this off just a bit. Yeah, let me put this one off just a bit. I'm sorry. I want to put this one in the next. I wrote it down there too soon. Let's put this as let's do this one, 2 to the k over 3 to the k. This one you can do two different ways. This one you could say, oh, you could use a ratio test because it has kth power. So let's try this one. And I'll get to the other one shortly. I think I can still get to it tonight. For this series, let's let, because it has k powers, that suggests things might cancel in a ratio test. Let rho be the ratio of successive terms. On the bottom, we put the one we have, 2 to the k over 3 to the k. And on the top, we put the next term, 2 to the k plus 1 over 3 to the k plus 1. We just replace k everywhere with k plus 1. And then we take the limit. This is the ratio test. You compute rho as the limit of the ratio of successive terms. If that's less than 1, you have convergence. If it's bigger than 1, you have divergence. If equals 1, you just go try something else. Well, what is this? Top times bottom over middle times middle. Rho is equal to limit as k goes to infinity. 3 to the k, 2 to the k plus 1 over 3 to the k plus 1, 2 to the k. That's just algebra at that step. Now, more algebra, limit k goes to infinity. 3 to the k, 2 times 2 to the k. All right, 2 to the k plus 1 is twice 2 to the k. Over 3 times 3 to the k. That's 3 to the k plus 1 times 2 to the k. Now I can cancel things. I can cancel 3 to the k with 3 to the k, 2 to the k with 2 to the k. And this is the limit of 2/3 is just 2/3, right? Rho is less than 1. Therefore, you get convergence by the ratio test. There it is. Questions on that one? If you see powers or factorials, and some other things too, often a good thing is the ratio test because you get those powers or factorials to cancel things. But there's another test we could use for this. What's another test? And a lot of it, there's more than one way, and on the exam when that comes up, you can use whichever test you want, but I'll maybe give you a hint on most of them. Alternatively, what could I have done? I could have said sum 2 to the k over 3 to the k. You recognize this is another case? How about rewrite it like this? Sum k equals 1 to infinity, 1 times 2/3 to the k, right? That's a geometric series with a equals 1. Well, the geometric series has to start at 0. But a equals 1 and r equals 2/3. It's a geometric series less the first term. Actually, if you rewrite this, we could rewrite it specifically as a geometric series and actually evaluate its sum. So I mean, it's geometric less the first term. One term does not affect convergence. Since the geometric series has r less than 1, it converges. If you want to be more specific, you can re-index this, let n equals k minus 1, and then you can write it specifically in the geometric form and just put a over 1 minus r and evaluate the sum also. This one I was just saying, does it converge? All right, so there's 2 different ways to do that one. Oh boy, I was going to start alternating series, but I think I won't get there tonight. All right, so let's just finish up this section. This is the same section as last time, so we didn't get real far. But I think this is a real important thing to go through and get all of these. Yeah, let's just go with the same problems we had last time out of 9.4. Finish those up, and I'll do 9.5 on alternating series next time. Just want to make sure I got my section straight here. Yeah. So no new homework, just finished 9.4 and be able to take a quiz on problems 9.1 through 9.4, just extra credit quiz, 10 points at the end. And those of you who want to show up for class, it'd be nice to meet you. Any last comments? Okay, well, have a good evening and a good weekend then.